Welcome to class. In this video, we get to talk about one of my favorite topics in differential equations, systems of them, starting with first order ODEs. A system of differential equations at the end of the day is what you would likely expect it to be. It is a list of several, here I've listed n different equations that all have to be solved simultaneously for n dependent variables. Each of those dependent variables, however, still only depends on a single independent variable, hence why this is a system of ODEs. And it is first order because every differential equation that shows up is first order. All of our other adjectives apply. If these functions f1 through fn happen to be linear functions, then we would call it a linear system if it applies globally to everything in the system. Oftentimes, you'll see these condensed because the writing gets to be a lot in vector notation. So I can write this entire system as the derivative with respect to t of vector u, where here u is, if you prefer vector notation, the vector u1, u2, down to un, or u1 x1 hat plus u2 x2 hat, and so on. And f, vector f is similarly f1 of t vector u, f2 of t and vector u, so on and so forth, down to the last one. And now you can see we can write this as the vector of derivatives equals the vector of right-hand sides. Don't panic with how cluttered the screen looks. I just wanted to show you an example of what I was talking about with all those adjectives we've learned so far still applying to a system. So just like we would write a single ODE is linear if we can write it as highest order derivative equals a big combination of all the lower order derivatives, but none of the coefficients involve independent variables. If I can do that for every equation in the system, we say the system is linear. So here, this is still just first order, but I have many variables, dependent variables, I should say. So here, when I have du1 dt, notice that every coefficient on every, oh, and excuse me, a little typo here, that as I look from every term, u1 to un, none of the coefficients depend on my independent variables, only on t. Here, the subscripting. The first subscript is saying that this goes with the equation for u1, and the second subscript is saying this is the coefficient on u1. So over here, a1n means it is the coefficient of un in the equation for du1 dt. And then, of course, I may just have some t's floating around after that. If I can write every equation in the system this way, we say it's linear. By the way, the advantage of the vector notation is I can compact that a lot by saying that the derivative of vector u with respect to t equals a matrix A that only depends on t. Here, of course, A would be the n by n matrix A11, A12, so on and so forth. And adding that vector f of t. Writing it this way makes it a lot easier to write down the definition of homogeneous, because if vector f is 0 everywhere, that means every single one of these little, or scalar f's, is 0 everywhere. That means every individual equation is homogeneous, so the full system is homogeneous. Because the pattern is sort of to just extend these ideas n times over, a lot of the same nice results we saw for single ODEs apply to systems as well. That is, so long as everything is sufficiently continuous and differentiable and all that, I'm not going to get too into the weeds on all of those assumptions, but they have solutions. So u equals au plus f has a solution. again, this is the first order system of n linear equations. So all linear systems have solutions. Second of all, IVPs, so if I add the initial condition that vector u of 0 is vector u naught, remember this is kind of like specifying n initial conditions, or one initial condition for each of the n first order equations. So if I have initial conditions, it has a unique solution derived from the general solution. Has a unique solution of the form general solution. Moreover, if u1 and u2 both solve the system of differential equations, I have a principle of superposition. Their linear combination is also a solution. Principle of superposition still applies here, just n times over. And really, that means that finding solutions to these guys should look very similar, at least logically. But the mechanics of how we're going to extend from one equation to many changes quite a bit.